First, we're going to talk about how they recognized acids before there were they knew much about chemistry. How they know something was an acid. Okay. Well, the most basic way is the acids taste sour. Kids, don't try this at home. Okay. Do not say, oh, is this an acid? Let me taste it. No, that's a bad technique. But if you taste something and it's sour, it's got an acid in it. Okay. And so our taste is one of our body's two chemical detectors. Smell's the other. And they taste sour. Acids conduct electricity when they're dissolved. Some are weak electrolytes, some are strong electrolytes. So, and that makes them weak acids and strong acids. Remember Friday, I warned you a lot about the sodium hydroxide. I didn't warn you about the vinegar. That's because vinegar was a weak acid. I was much more worried about the base. Here's something we learned about them, and you may have forgotten. They react with metals to form a hydrogen gas, because that's a single replacement reaction. Metal plus H something, the metal replaces the H, the hydrogen comes out. In your lab, you used the indicator phenolphthalein. Earlier we'd used litmus, gave it the litmus test. You use litmus paper. Litmus is actually just a chemical that they soak into the paper and then let it dry. That's how you make litmus paper. So up here I have some litmus. So here's some litmus. It's a purplish color when it's neutral. And if I add a little bit of acid, here's an acid. They call this color red. It's really pinkish. Okay. So, and we saw that earlier. We did a lab. We saw the litmus change color to tell us what it was making with the alkali metals. And we spent a lot of time talking about they react with hydroxides to form water and a salt. Okay, so you're copying furiously. That means acid plus base makes water and salt, which it's done over and over again. That was our neutralization reaction. Okay. That's what makes something, that's how we know something's an acid. Okay. Properties of bases. Hey, they react with acids to form water and a salt. It seems like I just wrote this seconds ago. If you put those two sentences together, what can you conclude? If hydroxides react with acids to form water and salt, and bases react with acids to form water and salt, what can you conclude? Hydroxides are bases, right? Our tongue detects bases as bitter. Don't try that at home. You know how you don't like things that are really sour and really bitter? That's because things that are acidic and basic tend to be poisonous. It's a survival thing. You don't want to eat too much of things that are sour or bitter. That's why we evolved those pieces, is so we didn't die. Things we like, sweet and salty, are things we need. These feel slippery. Don't try that one at home either. They can be strong or weak electrolytes. They change indicators. They change litmus blue. So here's my litmus. You know I put acid in it now. If I put base in it, and they call this blue, it looks purple though, right? That's because it made it blue with the red stuff behind it. I mean, they call this blue. It's not blue. And the phenolphthalein we saw was clear in acid and pink in base, right? Yeah. So we knew we had too much base in our lab. Because when I asked you for what an acid base was, that's the first definition of acids and bases. But when they made that definition, they ran into some problems. They recognized them right away. And that was, there were some things that were bases that weren't hydroxides. And things that were acids that didn't have hydrogen in them. Okay. So what you learned, what you wrote down in your Bell work was the first definition, the one that come up with a man whose name was Arrhenius. So you learned Arrhenius's, so what you wrote for the Bell work today was Arrhenius's definition of acids and bases. So I suspect strongly this is what you wrote for the Bell work today, because that's what I taught you so far. Acids have H's, bases have OH's, you put them together, you make HOH. There's a few problems with this, with these two definitions. One is, according to them, you can't have an acid or base unless you have water, which isn't true. And there's only one kind of base according to Arrhenius. It's something positive next to OH minus, right? Something positive and then OH minus. A metal, a polyatomic ion. Okay? But they could recognize there was a problem with their definition too. Okay? Use phenolphthalein. There we go. So be recognized right away. Okay. So here's where they recognize the problem. Got some water, and I put in a couple of drops of phenolphthalein, the stuff you used in your lab on Friday. Okay, and what's in this dropper is ammonia. Okay, it's ammonia, which is NH3 bubbled into water. Okay. How does NH3 become a base? Ammonia feels slippery. How is it a base? Okay. How does it match those definitions? How does NH3 produce hydroxide ions when it doesn't have any oxygen in it? See why this definition doesn't work? Because whatever's in here is a base. And that definition doesn't explain why it's a base. It does all the things that bases do. Okay. So That really gave them difficulty. How is NH3 a base? Okay. So they investigated what was really going on inside that reaction between acids and bases. Okay. And a couple other people came up with a new definition. And their names were Bronsted and Lowry. Oops, I forgot the umlaut. It's not an umlaut. There we go. Bronsted and Lowry. And they had to come up with a definition that could cover all the acids and cover all the bases they knew about. And what they said is, an acid is a proton donor and a base is a proton acceptor. And a proton is a hydrogen ion. And a hydrogen ion is a proton. Right? So it makes sense for the acid to be the proton donor, because acids have H+. What do you mean the base is the proton acceptor? Well, what Professor Lowry says, you can't have an acid without a base. You can't have an acid without a base. You have to have something that gives and something that takes. Because you got something that gives and there's nothing around that takes it, it can't give it away. Okay, so everybody knows HCl is an acid. What does it donate its proton to? There's got to be a base. But if I get an HCl solution, it's going to taste sour. It's an acid. What's the base in there? And the answer is the water. When HCl is an acid, when it dissolves in water, it gives the proton to water. Because water's got an H+, or the hydrogen ion's got an H+, water's got a negatively charged oxygen with a couple of lone pairs sticking up there. So there's places for that H to attract to. That positive charge is going to be attracted to that negative oxygen. Oops, my arrows are supposed to be lower. Something happened here. And the HCl gives its H to water, you make H3O plus and Cl minus. Okay, I haven't used these arrows, just to mention them a couple times. These arrows means if this is reversible. That I can go this way, or I can go that way. And what we've noticed about acids and bases, I get to go back and forth as many times as I want to, right? It's reversible. It goes both directions. Depending on what I pour in, I can make it go either direction. Okay? So water is a base. It took the H+, so it's a base. This is a base. And that H3O plus is called the hydronium ion. And yeah. They appear similar, yeah. Yeah, they're destroying cells. If you tear the cell wall, all the stuff oozes out, and you get all that stuff running. Yeah, it's just destroying cells. You know, because either one's going to tear apart the proteins and the fats. It's nasty stuff. Okay, so that was our definition. Oh, we already went through this. Oh, I already fixed it once. Oh, sorry. So in general, they always come in pairs. So you're going to have H next to A. A is going to be some anion. And the acid, the HA, hydrogen and an anion, is going to react with the water. The water's taking the H plus, and I end up with the anion by itself. So they always look like this. And what I've got there is acid, HA, plus base, H2O. And on the other side is acids and bases too. You got to have a pair on the other side. Okay? If I go the other direction, the H3O plus is giving away the H plus. If I go backwards, the hydronium ion is giving away the H plus. So the hydronium ion is the acid. And the A minus is taking that H. So the A minus is the base. So we got a pair of acids and bases on one side. We got a pair of acids and bases on the other side. And conjugate means the other form of it. So what the conjugate means is H2O is the base form. H3O plus is its conjugate acid. There's a base form and an acid form of everything. Okay? H2O is a base, or HA is an acid. A minus is its conjugate base. So there's a pair of acids and bases on one side, there's a pair of acids and bases on the other side, and an acid on this side is a base on that side. Does that make sense? Just depending on which way you go. Okay. This is an equilibrium. That means if I do anything to mess this stuff up, it's going to get back to some place where it's balanced. But this can run both directions. Okay? So that's the general equation for an acid. Here's the general equation for a base. We're going to let B stand for base. It doesn't stand for boron here. B stands for base. When bases are put in water, they steal the hydrogen off of water. And when you steal the hydrogen off of water, you're left with hydroxide. So if B is my base, what is H2O? H2O is my acid. It gave away an H, right? So B's my base, water's my acid. And on the other side, if I went the other direction, BH plus would give away the H, so it's an acid, and OH minus would pick up the H. It would be the base. And the conjugates, B is the base form, BH plus is the acid form. H2O is the acid form, OH minus is the base form. We got that pair going across too. A pair on each side and a pair across. An acid form and a base form. Okay, guess what that explains? That explains NH3. This is how NH3 is the base. The NH3 reacts with the water and ammonia makes ammonium. And water makes hydroxide. And that's why this is purple, or this is pink. See how this explains what base is better than the Arrhenius definition. Okay with that? Now, there's still one thing that we haven't explained. We need a third definition. Won't get it today, but there's going to be a third definition because ever put metal in your mouth? Doesn't it taste sour? Taste acidic? Okay. How's a piece of metal giving off hydrogen ions? See what's the problem here? So, you get a piece of foil in your mouth and get that sour taste. That means it's an acid. How is that an acid? How's a piece of aluminum an acid? We need another definition. We don't need it today, but I just want to let you know that there is another definition that's even more general than this. Okay? So, but first, identify the pairs. Cn minus plus H2O makes HCN plus OH minus. So Cn minus is, well, what happens to Cn from here to there? It picked up an H, right? And things that pick up H's, H pluses are bases. The H2O lost an H. Things that lose acids are acids. Lose H's are acids. Okay. Now on the other side, going this way, HCN gives up that H, so that's the acid. OH minus picks up the H, so it's the base. So we say that Cn minus is the base and HCN is its conjugate acid. H2O is the acid, OH minus is its conjugate base. Okay, that. Okay. So, we can write the equation for this and then identify the conjugate acid-base pair. Oh, what the heck was that? That is not what I clicked on. Okay. Well, we've done this a few times. We know we're going to make HOH plus Ca next to NO3. Ca is 2 plus, NO3 is 1 minus, so it's got to be CaNO3 2. And I have to do that. I can't stand not to balance them. Okay. But is that what really happens? Is there really any HNO3? It's H plus and NO3 minus. And there's Ca2 plus and OH minus. And there's water, and there's Ca2 plus and NO3 minus. So what donated the H plus? Well, that would be the HNO3. What accepted the H plus? Depends on if you look at the overall equation or the bottom one. It's the OH minus that took it. So you can either say that calcium hydroxide was the base or just the hydroxide was the base. Okay. Now go on the other side, go in the other direction. Water is an acid. What's the base? Well, going this way, what picked up an H? Well, the only thing I can see is HNO3, right? So that NO3 minus would be the base. Because going the other direction, it picked up an H plus. Okay. Extra super hard. Have you noticed we have a contradiction? You say, what do you mean we have a contradiction? What is water? Is water a base? Or is water an acid? The answer is yes. Depends on what you put it with. Because it can do both. It can accept a proton or it can donate a proton. So it depends on what you put it with. Oh, that's the wrong one. Thought I had the right one. Oh, there it is. Okay. Fact is, water ionizes all by itself. What really happens is H2O plus H2O makes H3O plus OH minus. And this is reversible. So this has water acting as both an acid and a base. Chemists are too lazy to write H3O plus. They are. They know it's there, but they really only write H plus. So when somebody writes H plus in water, there is no H plus in water. It's H3O plus. But we're too lazy to write. Okay? This is called the self-ionization of water or the auto-ionization of water. Because the prefix auto means car. No, prefix auto means self. So if I've got water, it's making ions. That means water, when it falls apart, will conduct electricity. But all year long I've said water is a lousy conductor of electricity. Because only a tiny amount of this happens. Tiny amount, 1 out of every 50 million fall apart. So you don't get a lot of ions, you get a few ions. So electricity can get through, but it's got to force its way through. But when it gets to you, you're full of electrolytes. The electricity would much rather go through you than the water. So when they drop the toaster in, we're not worried about the toaster or the water. We're worried about you. Don't eat toast in the bathroom anyway. It gets soggy. So in water, in pure water, the H plus concentration, that's what the brackets mean. The brackets mean concentration. The H plus concentration has to equal the OH minus concentration. Because when water falls apart, I make one of each. And it works out to be 10 to the minus 7th molar. That's what makes a solution neutral. A solution is neutral if it's 10 to the minus 7th molar. And that's not the only thing that's true. What if it's not neutral? How are those other numbers going to relate to each other? Well, if you take the concentration of the H plus times the concentration of the OH minus in water, it always equals 10 to the minus 14th. At 25 degrees Celsius. K for constant, W for water, the constant for water. Actually, it's called the ion product constant. Because the math you did was multiplication, and the answer to a multiplication question is a product, right? And what did you multiply? You multiplied ions. So the ion product constant for water is 1 times 10 to the negative 14th, and that's why neutral solution is 10 to the minus 7th. Because if you've got H plus equaling OH minus, then H plus squared equals 10 to the minus 14th. Take the square root of both sides. H plus equals 10 to the minus 7th. So that 10 to the minus 7th is really just an outcome of this. So in every aqueous solution, H plus times OH minus is 1 times 10 to the minus 14th molar squared. Nobody ever writes the molar squared. This is the one time they always write the units. This is one place they got lazy. They never write those units. So if the H plus is bigger than, concentration of H plus is bigger than 10 to the minus 7th molar, then the OH minus concentration has to be less than 10 to the minus 7th molar. What's a number bigger than 10 to the minus 7th? May think of a number? 10 to the minus 6, 1, right? Any positive integer, any positive number, anything bigger than 1/1,000,000th? No, 1/10,000,000th, sorry, 1/10,000,000th. We have a name for solutions that have more H plus than OH minus. We call them acids, an acidic solution. And if the H plus concentration goes down, the OH minus concentration has to go up because they got to multiply to 10 to the minus 14th. So if I have just a little bit of H plus, I'm going to have lots of OH minus, and my solution is going to be basic. It'll turn blue in litmus, pink in phenolphthalein. So if I know H plus, I know OH minus. When you have to do this math, remember the tricky thing is you write to type 10 to the minus 7th in your calculator, you type 1e negative 7th, not 10e negative 7th. So if the H plus is bigger than 10 to the minus 7th, it's acidic, and if it's less than 10 to the minus 7th, it's basic. Or you can say if the OH minus concentration is low, it's acidic, and if the OH minus concentration is high, it's basic. See, we're talking about completely different, in a different way than we were talking about acids and bases before. We're talking about as whole chemicals, not just as the ions. Okay, and now I'm going to bring up a topic I'm sure everybody's going to enjoy. I'm sure it's your favorite. You studied it before. You love it. The logarithm. This is not math class. You cannot talk about logarithms. It's not math class. Well, you've talked about logarithms before without even knowing it. Okay. All right, so I'm going to give you a quick review of logarithms. We're only doing common logs. So our logarithm is a power of 10. The logarithm is an exponent. That's what it is. It's an exponent. And you guys have calculators. To you, multiplying 6.7 times 10 to the 23rd plus 4.8 times 10 to the 15th is not a problem. You just push buttons. But I was in the first class in my high school that was allowed to use a calculator. Before that, you had to do it by hand, or if you got really big numbers, you used a slide rule. And what a slide rule had was 2 log scales that you slid. Okay? And what it gives us a way of doing is a way to write a shorthand for a really big or really small number. So I want to show you how logarithms work. Most of you think of it as a magic button you push on your calculator. It's not a magic button. Let's see how it works. So why don't you go ahead and get out your calculators and find the log of 2. The log of 2 is 0.301. Everybody okay with that? Is that what you got on your calculator? Okay. Now do the log of 200. And while you're pushing buttons, I'll say it's 2.301. How about the log of 2 million? Don't take so long, it's 6.301. How the heck are you doing that? Ooh, how about the log of 1/2? 0.699. How could you, do you think I've memorized the log tables? I have not memorized the log tables. How can I do that math in my head so fast? Well, because I remember how logarithms work, right? The log of 0.5? Oh, -3, -0.301? Okay, that's right. So you're right, -0.301. I think what I was, oh, okay, that's what it is. So try the log of 0.005. Why does that work? Well, I'm going to do this. This is the log of 2 times 100, right? Remember, logarithms are exponents, and in exponents, multiplication is addition. So it's the log of 2 plus the log of 100, which is the log of 2 plus the log of 10 squared. What power would you have to raise 10 to get 10 squared? 2. 0.301 plus 2 gives me 2.301. So next one, this is 10 to the 6th times 2. The 2 part is the 0.301. The 6 is the 10 to the 6th. That makes sense? Okay. The mantissa and the ordinate. Oh, no, we don't need to know the names of them. But what part is telling me about the 2? Well, it's the stuff after the decimal point, right? So the stuff after the decimal point is telling me about the 2? So the stuff after the decimal point is the only sig figs. That 6 doesn't tell me anything about sig figs. It tells me where the decimal point is. So the rule for sig figs is, if you take a logarithm, your sig figs are after the decimal point. And when you can come out of a logarithm, your sig figs are as many as their decimal places after the decimal point. Because that's the way logs work. The number in front doesn't tell you anything about number in front doesn't tell you anything about how many sig figs you have. It tells you where the decimal point's at. Okay. And that's what how slide rules worked, is by sliding around, you're actually adding up the logs. Okay. Why the heck are we learning logarithms? It's not a math class. Because to a chemist, the letter P means the negative log of. So the negative log of the hydrogen ion concentration is called pH. So you learned pH is a number from what, 0 to 14 with 7 in the middle being neutral? That's not what it is. First of all, it doesn't go from 0 to 14. Right? And 7's not always in the middle. Neutral's not always 7. If I change the temperature, neutral's not 7. Okay? But at room temperature, a neutral solution, we said, had a concentration of 1 times 10 to the minus 7th. And the negative log of 1 times 10 to the minus 7th is 7. In an acid solution, we said you had a number bigger than 10 to the minus 7th, right? The H plus is bigger than 10 to the minus 7th. Since pH is the negative log, I've got to turn my greater than sign around, right? So I could say the pH is less than the negative log of 10 to the minus 7th. So you have a pH of less than 7 if it's an acid. In a base, it's bigger than 7, but it's not 14. It doesn't stop at 14. How can I convince you it doesn't stop at 14? Well, what would the pH be of 1 molar HCl? Well, that means I'd have 1 molar H plus, right? And the negative log of 1 molar H plus is 0. So 1 molar HCl has a pH of 0. 10 molar HCl? 10 molar HCl would have a log of, negative log would be -1. You can have negative pHs. You just don't want to stick your finger in them. Does that make sense? And you can have pH is bigger than 14. Okay. To figure out pH, oftentimes we need to figure out pOH. P stands for the negative log of. So pOH is the negative log of the OH minus concentration. So P always stands for the negative log of. So what would the negative log of nut butter be? How do scientists do negative log? P, nut butter. The negative log of nut butter would be P, nut butter. P always means negative log of. Because if you don't have a calculator, dealing with these numbers is going to be tough. And you got to deal with them all the time, because at least one of them is going to have a big negative exponent. Right? because the H plus times the OH minus has got to be 10 to the minus 14th. And if I take the negative log of both sides of that, the negative log of H plus is pH. The negative log of OH minus is POH. And we're multiplying, but we do switch to logs. With logs being exponents, instead of multiplying, we add. So it's pH plus POH. And the negative log of 10 to the minus 14th is 14. So the pH plus the POH always equal 14. We'll practice the math side of this tomorrow. Today you're going to look at the equations, identify conjugate acid base pairs, those pieces. Okay? And we'll start laying down the log tomorrow.